Hello and welcome to our lecture on optimization. And so optimization is the core of the way deep learning, machine learning, AI occurs. Without optimization, there is no way that you can train these models. It would be intractable, as they would say in machine learning. So let's go through a little bit of the background and the history of optimization to understand what's coming in the future and what the limitations are. And so if you go back to pre-1900s, 1910 or something like that, and backwards, there were no computers. It was impossible to train these models like we do today. And so everything was a closed form solution. And so it was an analytical form. And so if there wasn't, Newton had this Newton-Raphson method to be able to find the minimum of a function, a global minimum of a function, but it had to be done in a very careful way. And so we'll talk about first closed form solutions. And so this is like pre-1920 backwards. And this basically means, let's say our regression example where we had, housing prices, and we want to fit the best fit line, h theta here, it's a function of x, and to these data points. And so if I represent my data points as x here, x1, x2, x3, and I have my truth label y. And so I have y, y1, y2, which is the prices, y3, etc. And we talked about the L2 norm before, and so that's basically I have something like the sum of the squares. So I have my y minus my h theta of x squared, which is equal to the L2 norm of y minus h theta. Same thing. Just do this correctly here. Squared. L2 norm, same thing. And so there is actually a closed form solution for this. And so if you break this thing out, we can get into it a little bit, but what you're going to do is you're going to take the derivative and set it equal to 0. And so you take the derivative of this thing. This is a matrix gradient. Don't worry about this. For the mathematicians out there, take this and you take the respect to 0, and you're going to have this piece here, and you set it equal to 0. You're going to end up something with the normal equation, which is x transpose x minus 1 x transpose y equals your theta star. It just so happens, just because this is a convex problem, and there is a closed form solution for it. And so, boom, done. That's everything. I don't even need to run SGD. I don't need to start at some random point. I don't need to get down to here to try to find this minimum. It automatically finds that minimum because it's the only point where the derivative is equal to 0. Done. But if, God forbid, there wasn't a closed form solution for it, how could I do it? I couldn't do this SGD unless I had a computer, and I could iteratively solve this very quickly. And so after really World War II, there was a little bit before, but with the advent of World War II and launching rockets, the only way to solve the trajectory problem was with computers and closed and open form solutions. And so we'll talk about that a little bit here. But if I had any more difficult of a problem, I wouldn't be able to solve it. And so instead, what they said, okay, fine, I can't find a closed form solution for a more difficult problem. What I can do is I can put this problem into standard form, which we're going to define right here. I'm going to minimize theta, minimize this objective with respect to theta, subject to some constraints. And there's a bunch of rules that if my objective and my constraints follow those rules, then this can be solved. Then it's solvable, and I can put it into something called convex CVXPy or convex solver, and I can solve it. using either SGD or some other method, interior point methods, all these different solvers to actually find theta star. And the goal is to find theta star that gives me the minimum value of my objective. And then equivalently, it's the same thing to say minimum versus maximum. We would just do the negative of the objective, the same exact thing. The theta stars would be the same, subject to the same constraints. And so typically it's just minimization and all that kind of stuff. And if you really want to learn about this, all of the guy that wrote the book on convex optimization, and he's a professor at Stanford. I took his course. His name's Stephen Boyd, and he's fantastic. And all of his stuff is online, so you can learn convex optimization from the guy that wrote the book, which is and all the lecture slides would be right there. They go into very mathematical analysis and things like that. You don't need to know that. You just need to know what is linear optimization, which if it's a line, then it's linear and it's solvable. If the objective is convex and there's a closed form solution for it, like regression, then you're all good. You don't have to use any SGD or anything fancy computers. If the objective is non-convex, or if the objective is convex but there's no closed form solution, then you need to use a solver like CVXPy, or many of the other solvers out there on the planet. That this is run by Stephen Boyd's group. It's very, very cool, very interesting. We use it all the time at Focal. And the last one is, and this is the not until, so just to keep the dates in here, I'll put here this standard form here. Now we're talking about, this is 20, this is 19, 20 and after, up until about 2012. To be completely fair, maybe 1990. The back prop paper was written in 1980, but really the computers weren't there, and so we couldn't do this stuff until, let's say 2012. So, and that's when the AlexNet paper was published. And so 2012 and after is all non-convex. And so previously, if we would, in standard form, they have to follow specific rules. The objective function has to be convex. The constraints have to be convex. If they're non-convex, there is no open form solution for it. You just can't solve it. You'd be stuck. You get stuck in local minima. But all deep learning is predicated on non-convex optimization, meaning that this is, this problem where I can't do my Newton-Raphson method where I start at any point and I iterate and I kind of get here and then I get here and then I get there. Well, that is far from the global minimum. This is called a local minima. This is the global. And your goal is to find the global because that's the right answer. That's the best answer you can find. In most of deep learning, there isn't one good answer. There's many different ways to beat Go, to play the game of Go, to win chess, to solve the cat versus dog. There's many different filter types that are acceptable. And so when we're talking about, that's what where SGD comes into play. And so we talked about this before, but SGD is stochastic gradient descent. Is when I want to iteratively, this is the nomenclature for update. I'll do minus theta this of my objective function, j theta. And that's all I do. I take a mini batch, I put it through here, I compute my loss function, j theta, I take the gradient of that, and I back propagate that with a little bit of a scalar here, 0.1 or 0.3, something like that, and I update my thetas. And now you may ask, okay, well, yeah, this is good to find the local minima, but how do you find the global minima? Well, what I do is I have a bunch of initial thetas. And so I have my theta 0, 1, I have theta 0, 2, and I try a bunch of different things all over the place. And so there's a lot of different ways, and maybe I just finally get into this one, and I start from there. And so that's a fine strategy to find my global theta, and you find the one that works the best. And there's tricks and tips to do that. The other thing that I can do is I can change this function, j theta, so that it becomes more convex. We talked about this earlier, but it's very common for deep learning engineers to use something called cross entropy versus the L2 norm we talked about before. And so if you go here, and I plot y minus y hat, that is a really rocky function because of this exponential. It looks like this, versus negative log of y hat looks kind of like this. And that's much easier to learn. And so we'll have less local minimas, easy to learn. And so you want to pick your objective function that will increase convexity and make it less and less non-convex. That makes a problem learnable or not. In reinforcement learning, you're taking a derivative against an environment which is highly nonlinear, highly convex, highly non-convex, and so it's really difficult. Why this matters for retail? In retail, we are typically, you'll find that we're going to try to optimize for, let's say we're trying to maximize EBITDA. EBITDA is revenue minus cost minus labor, SG&A minus, cost of inventory, cost of carry. Well, all of these terms they may be convex themselves, sometimes not, but the sum and subtraction of convex and non-convex numbers becomes highly non-convex. And so this plus that is not a convex function. And so this becomes extremely non-convex very quickly. And so this EBITDA, if you plotted it over all my inputs, which is, what are my inputs? I have price, I have the inventory that I'm going to carry, my forecast, whatever you want to call it, my shelf capacity, what I'm going to put on the shelf, my labor, all these different inputs. And so those are my thetas I'm trying to optimize for. And it's a highly non-convex problem. So this is why it's hugely important to use non-convex optimization in the context of retail. But if you can, try to use convex or linear optimization. All right, that is all I have. Thank you so much. We'll see you in the next lecture.